Alright, let's look at the last example here, example 25 that we have for 4.1. Once again, we have acceleration, we got to find velocity, and then we got to use velocity, find position in this problem. So once again, simple kind of physics type problem. We have the maker of an automobile advertises that it takes 13 seconds to accelerate from 25 kilometers an hour to 80 kilometers an hour. Assuming constant acceleration, compute the following. So part A, we need to find the acceleration in meters per second squared. Part B, we want to find the distance traveled during 13 seconds. Alright, so initially, we have our velocity and our initial velocities and things like that. Okay, so that's given. We know at time 0, okay, that it's going 25 kilometers an hour, right? That's a velocity. And we know at time 13, it's going 80 kilometers an hour. But we want to make sure that we are in meters per second squared. So we got to go kilometers to meters, and we got to go hours to seconds. Okay, so that's really all this first conversion is. We're going to take 25 times, there's 1,000 kilometers, alright, in 1 meter, and there's 3,600 seconds, okay, in an hour. So now that we know initial velocity, time 0 is 250 over 36 meters per second, and final velocity is 800 over 36 meters per second. Okay, we have to find acceleration using constant acceleration. So for us, that just means acceleration is equal to a. We're going to determine what that is, okay? And to find velocity, we are going to integrate acceleration. Okay? We don't know exactly what acceleration is, we just know it's constant. So that means there's no variable involved, we're just going to call it a. So we're going to integrate a to get velocity. When we integrate a with respect to time, so just notice that a is a variable just representing acceleration. dt is because we're going to integrate with respect to time. So when we do the antiderivative of a, it'd be like doing the antiderivative of 4 or the antiderivative of 10. The antiderivative of a is just at, okay, because it's with respect to time. And then we have the constant of integration plus c. So our velocity, our general solution for velocity with respect to time is at plus c. We're going to use our initial equation here, or initial conditions, sorry, to find out exactly what that c is. So we have a couple different ones here. When time is 0, we plug in 0, so a times 0 is 0. That equaled what? 250 over 36, so c is 250 over 36. Our other one, 800, equaled a of 13 plus c. Okay, we're going to substitute this in for our c. We already just found c. So we're going to use that to actually find this piece right here. Okay, so what 13a is, that's going to actually help us find what the value of acceleration is. So we can use both of these two initial conditions to find a. So we substitute in the first one because the 0 eliminates the a, and we know what c is. Okay, it should be the same for both because constant acceleration. So we use the other condition. When time is 13, we know that the velocity is 800 over 36, right? Plus c, we know what c is, we just found it. That c helps us find a. So it's 13a right here. So we subtract 250 over 36 from both sides and then divide by 13. So our acceleration ends up being 1.175 meters per second. Okay, so that's going to be important in the next part. We want to find position, right? Position means that we are going to integrate velocity to get position. Well, velocity is at plus c. Now we know what a is. We found a in part 1 is 1.175. So we're going to integrate 1.175t plus 250 over 36, right? Because that's our initial c right there. Now, when we integrate this, you guys should all be able to integrate this. We've done multiple examples integrating that. Now, the key is what? We have that other initial condition. Okay, our position, we know it's 0 at 0. It's starting, right? So that c is equal to 0. Then we substitute that in. So c is 0 here, And so our position equation is S of t equals 1.175 t squared over 2 plus 250 over 36t. We're going to substitute in our last time for as 13, because that's our other one. So the first one knocked out the c for us. The second one's going to actually tell us how far we traveled in 13 seconds. So we're going to substitute 13 in for t, and we end up traveling 189.58 meters. Alright, so let's just review this problem real quick. Alright, we had constant acceleration, which just means we needed to integrate a with respect to time. We integrated a with respect to time to find velocity. We used our two initial velocities, starting at time equals 0 and time equals 13, to find out what our actual acceleration is. Okay, our acceleration was given as 1.175. Then we integrate our acceleration equation, which was at plus c. We're going to integrate that, okay, because that's our velocity, using a and t and plugging it in. So once we integrate our velocity equation, we found our position. Once we knew our position equation, we used our initial conditions to find our particular solution, and then our particular solution, okay, we substitute in a time of 13 seconds to get our total distance. Okay, so once again, just like the previous example, we had to go from acceleration. We integrate acceleration to get velocity. We used initial conditions. Alright, and then we have our velocity equation, and we had to integrate velocity to get position. Once we had the position equation, we were able to substitute in the time to figure out how far we traveled. Okay, so we found the acceleration and we found the distance traveled in 13 seconds. Alright, if you guys have any questions about anything in section 4.1, go ahead and email me and I'll get back to you as soon as I can.